All right, formal charge is our topic for today. A subject you may or may not be familiar with from prior experience. Depends on what chemistry classes you've had. Formal charge is really important, so we're going to spend the entire lecture today talking only about formal charge and what we use it for and when it's to be pulled out and when we can just kind of not worry about it. So let's talk about what formal charge is. All right, so here's the basics. So not every single individual atom is neutral, even if the molecule itself is neutral, right? So a molecule as a whole could be neutral, but individual atoms may not actually be neutral. They have what's called a formal charge. If one of them is +1 and one of them is -1, they would cancel each other out, right? So the molecule would be net neutral, but not always the case, not always the case. In some cases, they're all 0. That's the ideal situation, but not always, okay? So not every single individual atom is neutral. And then, even though you have a polyatomic ion with a charge, only some atoms are the ones who actually carry that charge, okay? So why do we care about formal charges and where do they come from? Well, formal charge comes from, long answer, quantum mechanics. Short answer, electron density, okay? Where the electrons are hanging out. And so the location of that formal charge has a huge role to play in reactivity. If you go on to take organic, which I know based on the majors you guys have, majority of you people will, right? You're going to be seeing the role of that formal charge in organic reactivity big time. And we're talking all about covalent bonding still, right? This is all based on Lewis structures. So what's the point of formal charge? It's to figure out which atoms carry a charge, okay? It's a polyatomic ion. All of the individual formal charges must add up to the net charge. And if it's a neutral atom, all of the formal charges must add up to 0. So you must have some that are positive and some that are negative. For it to be neutral, you have to have all of them add up to the total charge if it's polyatomic, okay? And again, ask yourself, why am I doing this? I'm doing this because it has a huge role to play in reactivity. That's the final answer, right? The other reason why you do this is it helps you decide which resonance structure is favored and if we need to make some double bonds. So we're going to look at lots of examples today, all about formal charge. Today's entire lecture is about formal charge. So everybody with me here on what it is and why we care about it. Maybe you don't care about it, but I'm telling you, you have to care about it, right? It's going to be on the test. Is everybody with me? We good? Okay, so here's the formula for formal charge. I represent that as FC, okay? Because that's just a long word. FC is equal to valence electrons. How do you get valence electrons? How do you know how many valence electrons an atom has? Periodic table, right? So valence electrons minus 1/2 of the bonding electrons. So these are electrons that are in bonds minus the paired electrons. So these would be non-bonding electrons. Those would be lone pairs. Okay, those little dots sitting around that aren't doing anything, those would be your paired electrons. Electrons that are in bonds, those would be your bonding electrons. Valence electrons, that just comes from the periodic table. Okay, so valence minus 1/2 of bonding minus paired. VE minus 1/2 BE minus PE. Valence minus 1/2 of bonding minus paired. Now you assign formal charge to every single atom individually, okay? Every single atom individually gets a formal charge. It's not just the molecule as a whole. You've got to calculate it for each unique atom. Okay, then this is what I just said. The sum of the formal charges must add up to the overall charge. So if the molecule is neutral, right, it should all add up to 0. And if it's a polyatomic ion, they should all add up to the charge, right? So if you're doing ammonium, they should all add up to +1, right, when you add them up. If you're doing carbonate, right, they should add up to -2. If you're doing carbon dioxide, it should add up to 0. Okay, makes sense? All right, so let's do this example. We're going to start with ozone. O3 is the formula. So we're going to do each atom individually. First thing you have to do is you have to sketch the Lewis structure, okay? You can't do formal charge till you have a Lewis structure. Why? Because bonding electrons and paired electrons are part of the calculation. If you don't know how many bonding electrons you're dealing with, you can't do the calculation, right? So the first thing you need to do is you draw the Lewis structure. All right, that's step one. You can't do formal charge until you draw the Lewis structure. So what we did on Friday, right? Draw the Lewis structure, that's step one. So there's the Lewis structure. Now each oxygen atom is going to have its own formal charge calculation. So let's go through them individually. We're going to do a formal charge calculation for this oxygen, for the one in the middle, and the one on the right. All right, so let's start with the one on the left. We'll just work left to right. So these are the paired electrons, right? And these are the bonding electrons. How many electrons are represented in each one of those sticks? 2, right? So 2 and 2, right? And there's 1, 2, 3, 4. Okay, we established all that. Now let's think, how many valence electrons does oxygen have? Look at the periodic table. 6 valence electrons, right? So you take the number from the periodic table. So 6 minus 1/2 of the bonding electrons. Well, I've got 2, 4 in bonds. So 1/2 of that is 2. So 6 minus 2 minus the paired electrons. I've got 1, 2, 3, 4 paired electrons. Remember, you can think of paired electrons as the non-bonding electrons. Now, it's not number of pairs, it's number of actual electrons. Okay, so don't confuse pairs versus actual electrons. It's not 2 pairs, it's 4 total electrons. Okay, so 6 minus 2 minus 4, so that gives me 0. Right, so the formal charge on that oxygen atom is 0. Is everybody with me on the first one? All right, let's do the oxygen in the middle. Valence electrons, that hasn't changed, right, because it's still oxygen. So this number just comes directly from the periodic table. So there's no work in getting this first number. It's going to be 6 for this number too. I mean, for this oxygen too, right? All oxygens, 6. Now we're going to do the bonding electrons. We have to consider both sides, okay? 2, 4, 6, right? Don't forget about these. 2, 4, 6, because this oxygen is part of these 2 bonds on the left and this bond on the right. So 2, 4, 6. But I have to take half of that, right? Half of 6 is 3. So 6 minus 3 minus, how many paired electrons does it have? 2, right? 2 paired electrons right there on the top. So 6 minus 3 minus 2 gives me, what's 6 minus 5? 1, right? So the formal charge on this oxygen atom is +1. Did everyone see where this +1 came from? Valence minus 1/2 of bonding minus paired. 6 minus 3 minus 2 gives me 1. All right, now we're going to do the one on the right, far end here. Valence electrons, that's still 6, right? Because this is oxygen. Nothing's changed about that. So 6. It's only got 1 bond that it's working with, right? And that bond represents 2 electrons. So 1/2 of 2 is 1. And then how many paired electrons does it have? 1, 2, 3, 4, 5, 6. So 6 minus 1 minus 6 gives me -1. Right? 0 plus 1 minus 1, that adds up to 0. Correct? Ozone does not have a charge, right? There's no superscript here. It's not O3 minus 1 or anything like that, right? It's just O3. No charge. So all the formal charges should add up to 0, and they do. But just because the molecule is net, so let's go over the answer. First, you need a Lewis structure, right? Because you can't do formal charge if you don't know what the Lewis structure is. So we have to decide how many valence electrons we have to deal with, and then to pick who's in the center, and then we draw our Lewis structure. Just by looking at this, CH3O, who's going to be the central atom? Oxygen?
Yeah.
Are you sure? Well, let's think about that. Remember the electronegativity rules? Electronegativity rules, the least electronegative element is the central atom, right? Electronegativity refers to ability to share. So it's the least electronegative atom that goes in the center. So we look at the two, carbon versus oxygen, right? Oxygen is more electronegative than carbon. So it'll be carbon in the center. So you're close. Do you see why carbon has to be in the middle?
I thought it was the other way.
Okay.
I thought it was most likely.
Right, good. Okay, so carbon's going to be in the middle. We always know hydrogen can never be in the middle. Why? Hydrogen only forms one bond. Right. So there's the Lewis structure. Do we agree on the Lewis structure? Now, if you had, this is a hydrogen and your oxygen up here, that's the same thing. Now, here's something about formal charge. Okay, the formal charge for this hydrogen is going to be the same as this one and this one. Right? Why is this hydrogen's formal charge going to be exactly the same as this one and this one? Because it's a hydrogen with one bond and no lone pairs, right? So if you calculate it for this one, it's the same for the other two. So really you only have to do 3 calculations, right? This hydrogen, this carbon, and this oxygen. All right, so for oxygen, 6 valence electrons minus 1/2 of 2 minus 6. All right, so that's 6 minus 1 minus 6, so that gives me a -1 charge, right? All right, for the hydrogen, and again, it's going to be the same for this hydrogen as it will for the other two, because it's a hydrogen with one bond, hydrogen with one bond, hydrogen with one bond. We don't care what it's bonded to, we just care that it's a hydrogen atom with one bond. So hydrogen has 1 valence electron. There are 2 electrons in this bond, so 1/2 of 2 is 1, and there are 0 paired electrons, so 1 minus 1 minus 0 is 0. So that means this one's 0, and this one's 0, and this one's 0. All 3 of them are 0. And then for carbon, carbon has 4 valence electrons. It has 2, 4, 6, 8. 8 electrons in bonds, right? 1/2 of 8 is 4, and it's got no lone pairs, right? It's just a carbon atom with 4 bonds, no lone pairs. 4 minus 4 minus 0 equals 0. So 0, 0, 0, 0, -1. That's where that -1's being carried, right? And that's why the molecule has a net negative charge. All the formal charges added up give you the net charge on the polyatomic ion. If you made a mistake on this one, do you see where you made it? Makes sense? You have to start with the Lewis structure, right? And then do your formal charge assigning. All right, so like I said, on Friday, when do we use formal charge in this class? We're going to use formal charge to decide which resonance structure is preferred. We're going to do that today. And then we're going to use formal charge to decide if we need to make double bonds. Remember on Friday, I told you there are only 2 times that you're allowed to make double and triple bonds. Number 1, which we addressed on Friday, if the central atom doesn't have an octet, right? If the central atom, remember we did HCN, central atom doesn't have an octet, you got to make double and triple bonds. In that case, triple bonds. I also said you could use formal charge, though, if you're, if you can make double bonds if your formal charges are a mess. So we'll look at that scenario today. So first of all, we use this word resonance. We have to define that. So let's talk about what resonance is, okay? So here's the first scenario when we'll be using formal charge. We use formal charge to pick the best resonance structure. So what is resonance? It occurs when there's more than one possible Lewis structure. There's more than one possible Lewis structure. Okay? That's what resonance is. It happens when we've got more than one possible Lewis structure. So I'll give you an example of that. I'm going to write it over here because the camera does not like it when I write on the board. It gets really glitchy. All right, so for instance, let's do carbon dioxide, CO2. All right, carbon has 4 valence electrons, right? And oxygen has 6. So 4 plus 12 is 16. All right, let's draw the Lewis structure. Carbon's going to be our central atom. Connect with single bonds, 2, 4. Now give the outer atoms an octet. 2, 4, 6, 8, 10, 12. Okay, I'm out of valence electrons, and carbon, the central atom, doesn't have an octet. I'm going to have to make some double bonds or triple bonds to give the central atom an octet. Okay? What's one way I could do that? 2 off each side and make 2 double bonds, right? Or what's another way I could do it? Right, I could have a triple bond on one side and a single bond on the other, right? Both of those give carbon an octet. One is favored, one is not favored. How do I decide which one's favored? Okay, these two are called resonance structures. And formal charge allows us to pick which resonance structure is correct. Okay, that's what I mean by resonance. So we're going to use formal charge to pick which one's best. So the best resonance structure is the one where all our formal charges are 0, if that's possible, if it's possible. A lot of times, that's not possible in the case of, for instance, a polyatomic ion. Right? If it's a polyatomic ion, then there's no way everybody can be 0 because you're going to have a net charge. But if it's a neutral atom, a neutral molecule, right, best scenario is everybody's 0. But if that's not a possibility because you're dealing with a polyatomic ion, or even if you're dealing with a molecule where you just absolutely have to have formal charges, then your other option is you are always preferring small formal charges to large values, okay? So pick the resonance structure that has the smallest numbers. If you've got 2, 2, and 6 versus 1, 1, and 3, right, pick the smaller one. And then also, the negative formal charge needs to be on the most electronegative atom. Think about why. Electronegative atoms are ones that are greedy with electrons, right? They hold on to electrons tightly in bonds. They're not good at sharing. So that means if there's going to be a negative formal charge, that's a high electron density area. So that needs to be centered on the more electronegative atom. Electronegative atoms enjoy having that extra electron density around. Okay? So if there's going to be a negative formal charge, it needs to be on the most electronegative atom. So if you can't have everybody be 0, for instance, if you're dealing with a polyatomic ion, then you need to pick the scenario where we have the smallest formal charges and then we have a negative formal charge on the most electronegative atom. If you've got a negative formal charge on hydrogen, for instance, that's not good. That's not good. Okay, so this is the criteria that we use to decide which resonance structure is best. Because right there on the board, I've drawn 2 resonance structures. One is favored, one is not favored. We're going to use formal charge to decide which one is favored. All right, so 2 resonance structures of CO2 I just drew, right? Those are the 2 resonance structures. You can have 2 double bonds, 1 on each side, or you can have 1 triple bond and 1 single bond, right? So let's use our formal charge and decide which resonance structure is favored. All right, so let's deal with this one first, the 2 double bonds. Now, think about this. Do I have to do a calculation for both of these? No, I only have to calculate it once. Why? It's an oxygen with 2 lone pairs and 2 bonds, right? So that means this one's formal charge is going to be the same as this one. Now, if this one had 2 lone pairs, 2 non-bonding electrons, and this one had 3, I would have to calculate them separately. But since these 2 are identical, 2 lone pairs, 2 bonds, I can calculate it once, and I know it's the same for the other. So, formal charge is 6, because it's oxygen, minus 1/2 of 4, right? 2, 4. So 1/2 of 4 is 2. So 6 minus 2 minus 1, 2, 3, 4. So this one's 0, which means this one's 0 too. So now we're left to deal with is carbon in the middle. Carbon's got 4 valence electrons, right? Because its location on the periodic table tells me it's 4 valence electrons. 2, 4, 6, 8. So that's 8. When I take half of that, that's 4. So 4 minus 4. It has no lone pairs. So 4 minus 4 minus 0. So its formal charge is 0. And then we already calculated it here. It's the same, right? 6 minus 1/2 of 4 minus 4 gives me 0. So 0, 0, 0. Now let's do the other resonance structure. We're going to have to calculate both of these, right? Because these 2 are not identical. So we'll have to do the calculation twice. So let's do this one first. Oxygen is 6 valence electrons, 2, 4, 6, right? There are 6 electrons that are bonding. and there are 2 that are non-bonding. So 6 minus 3 minus 2 gives me plus 1. Let's do carbon now. Carbon's got 4 valence electrons, 2, 4, 6, 8. Right? So its formal charge is the same as it is here. 4 minus 0, so it's still 0. And then last one, 6 valence electrons minus, there are 2 in that bond, so 6 minus 1 minus 6, 2, 4, 6. So 6 minus 1 minus 6 gives me minus 1. So we've got positive 1, 0, negative 1 versus 0, 0, 0. Which one's correct? Which one's the favored resonance structure? The double bonds or the triple bond option? Double bond option, right, double bond option. Okay? If I put this on a test and ask which one's favored, students tell me a lot of crazy stuff. Like, oh, this one's symmetric. That's why it's the winner, right? Okay, it's not about symmetry. It's about formal charge. Okay, make sure you understand that. Any questions on this one? All right, here's one for you to do. I've given you the resonance structures. Which one's the correct one for nitrite? I'm going to pause the recording, give you some time to work on it. So, the answers are derived from formal charge, right? You don't just pick the one that looks most appealing visually. You have to base your calculation, you have to base your answer on the calculation of formal charge. You can't just pick one and go, I like that one better, right? You have to calculate formal charge. So, let's look at them. In this Lewis structure, we have 0, 0, minus 1, whereas in this one, we have 0, minus 1, 0. So they both add up to negative 1. Your decision now is which atom is better at carrying the negative charge, right? Because what's the rule? The negative formal charge needs to be on the most electronegative atom, right? So you're comparing nitrogen versus oxygen, right? In this one, oxygen carries the negative 1 formal charge, and in this one, nitrogen carries the negative 1 formal charge. So which one's more electronegative, nitrogen or oxygen? More electronegative? Oxygen's more electronegative, right? So that means that this one is favored, right? Because we want the negative formal charge to be on the most electronegative atom. So actually, this one's the winner, not this one, right? In the previous example, the 2 double bonds made the final pick, right? So that's why I keep emphasizing, you can't just look at it and go, oh, that one's symmetric, or oh, that one looks neat, right? It has to be based on formal charge calculation. If there's a negative formal charge, it needs to be on the most electronegative atom, which is oxygen. Oxygen is more electronegative than nitrogen. Does this make sense? If you made a mistake, you see where you made it? All right. Now, sometimes you have resonance structures that are equal, and there's not one that's favored. So let's look at an example. So this is sulfur trioxide. All right? We've got sulfur, double bond, single bond, single bond. And notice the double bond's on the left, it's on the right, it's on the top. Right? These 3 are equally favored. They're equally favored because you're going to have plus 2, negative 1, negative 1, 0. Right? So plus 2 offsets negative 1 and negative 1. So that's why it adds up to 0. And no matter which way you spin it, they're always going to add up to 0. There's not one that's got to be an issue. Okay? So it's not going to matter. All 3 of these are equally favored. Do you see why these 3 would all be equally favored? Make sense? So I'm going to ask you this. Does dinitrogen monoxide have resonance, number 1? And if so, is one of them preferred? Take a second and figure that one out. So to answer the question, does dinitrogen monoxide have resonance? Yes or no? Is there resonance? I came up with 3 resonance structures. And yes, one is preferred. There are 3 resonance structures. You could draw it Now, nitrogen's the central atom, right? Why is oxygen not in the middle? Oxygen's too electronegative compared to a nitrogen, right? So if you drew oxygen in the middle and you're like, oh, I want to be symmetric, O-N-N, right? That's not correct. Nitrogen's least electronegative, it goes in the middle. So I could have two double bonds, I can have a triple bond between nitrogen, nitrogen, or I can have a triple bond between nitrogen, oxygen. Those are my three resonance structures. One of them is strongly favored, okay? Why? Oxygen's the most electronegative atom, so it's the one that carries the negative formal charge. All right, do this one. Does HCO2 minus have resonance? And in this case, is one of them preferred? Take a minute and try this one. All right, let's go over this one. Does it have resonance? Number one. Resonance. Well, you could draw the double bond on the left or on the right, on the bottom, right? Depending on how you oriented yours. Is one of them going to be preferred? The answer is no, right? They're both equally favored because either way you draw it, it's going to add up to be 0, 0, 0, minus 1. 0, 0, 0, minus 1. So either way, you're not getting anything different, right? So no, in this case, both of them are equally favored. If you made a mistake on this one, do you see where you made it? Any questions on this one? This is the last one we're going to talk about in this section. We're going to move on to when to use formal charge to decide if you need to make a double bond. So we're going to shift gears in a second. Any questions on this part before we move on? Okay, so now let's talk about the scenario that occurs when we use formal charge to decide if we need to make a double bond, right? Remember on Friday I told you there are only 2 times you're allowed to make double bonds. One of them is because the central atom doesn't have an octet. So you've got to give the central atom an octet using double or triple bonds, which a lot of times creates resonance, and then you'd use formal charge to pick the one that's correct. Or, I said, you're also allowed to make double bonds if your formal charges are a mess, and adding a double bond makes your formal charges better. Okay? Those are the only 2 times you're allowed to make double bonds. Extra electrons are never dumped into a double bond, right? They're just put on the central atom. So let's look at this one. I mean, I ask students to draw sulfate, and 99.9% of the time, this is the answer I get. Right? Sulfur's got 6 valence electrons, oxygen's got 6 valence electrons, and there are 4 of them, plus the charge gives me a total of 32. Now, if you're just looking at this, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. If you're just looking at that as an uninformed person going, okay, there are 32 valence electrons, nothing's weird looking, normally just looking at that, right? If you don't know anything about formal charge, you jot this down and move on, right? But let's look at our formal charges and see why this is not the correct answer. Okay? If you look at your formal charges are -1, -1, -1, -1, and +2. So -1, -1, -1, -1, and +2. There's nobody that's got a 0. Everybody's got at least a charge of some sort. -1, -1, -1, -1. Now, granted, those -1s are on oxygen, which is more electronegative than sulfur, but still, the point remains is that everybody's got a charge. Everybody's got some sort of charge. So what if we made some double bonds? What would happen to our formal charges then? What if we, instead of having 4 single bonds, we had 2 double bonds and 2 single bonds? Let's see what that does to our formal charge. So now we end up with 0 on the central atom, 0 on this oxygen, 0 on this oxygen, -1, -1. -1 plus -1 adds up to -2. Ta-da! This one still adds up to -2 as well, but look at how we had to get there. -4 minus 2 gives me -2, versus 0 plus -2 gives me -2. So which one is favored? This is the correct Lewis structure for sulfate. Okay, so that's why I say on my How to Draw Lewis Structures handout, right? That on there so everybody can see it. Number 6, evaluate your structure using formal charge. So once you've drawn your Lewis structure, like this, let's pretend I asked you to draw a sulfate. This is what your default setting would draw, right? If you don't know anything about formal charge, and all you know is just make all your valence electrons represented, go back and look at that and go, you know what? Everybody's got a charge here. I wonder if adding a double bond or maybe 2 double bonds might give some of my atoms a 0. The answer is yes. This is the correct Lewis structure. Okay? Do we understand why? So we're allowed to add double bonds if your formal charges are a mess and those double bonds make your formal charges better. Okay, so there's our comparison. 0, 0, 0, -1, -1 versus a bunch of negative ones and a +2. All right, so here's one for you. Draw the Lewis structure for sulfur dioxide. Then ask yourself, can your structure be improved through double bonds? And then correct it. I'll give you a minute to do that one. Okay, solution here. So that's the original Lewis structure. Yes, sulfur in the middle, 2 oxygens, 1 double bond. If you make 2 double bonds, that gives everybody a 0 versus 0 + 1 - 1. Is that what you came up with? Now, if your modification causes the central atom to take on an expanded octet, that's okay. Okay, because if you think back to our sulfate example, oops. In our sulfate example, right, that modification made the central atom take on an expanded octet, 2, 4, 6, 8, 10, 12. That's okay. Okay. So if your modification makes the central atom take on an expanded octet, don't freak out about that too much. Okay. There are some times where that would not be okay, but I don't think in this class I'll give you some where you'll get into trouble from that. Questions? So here at the end of this, I have some review problems we could do. Do you want to do them? You want to jot them down and try on your own? Or is your brain completely fried? Or you just not care? That works too. That's an option too. I just don't care, Dr. Brett. That's good too. All right, well, I'll stop the recording then.